Okay, so before we talk about how do glaciers move, I want to go back to a previous slide in one of our other lessons in which we talked about igneous rocks. And we said that igneous rocks came from a magma. And so we had this picture that showed the pressure as a function of temperature. So temperature was going sideways and then pressure was going down. So that up here, this represented the surface of the earth. And then as you go down into the earth, the pressure increases. And the reason why the pressure increases is there's more stuff on top of you. So at this depth here, you have the weight of all of this material on top of you, and so the pressure increases. And then in this picture, it shows a line that looks like this, and then that represents the boundary between liquid magma and solid igneous rock. So that, let's say that we're at a certain depth here, and then the temperature is cold. So we're going to plot right about here where there is pressure because we're under the ground, but the temperature is relatively low. So temperature increases as you go this direction. So then that means that under low temperatures, this material is going to be a solid. But if we were to increase the temperature, and so that means now that we're moving in this direction on the graph, eventually this solid rock would turn into liquid magma over here. So this would be magma, and then this is solid igneous rock over here. So what I wanted you to see is that substances can either be a liquid or they can be a solid depending on their pressure and on their temperature. So let's compare that then to this picture here, which shows how the pressure and the temperature change on water. So this was for igneous rock, and notice we can have a similar looking kind of picture that goes with water. And so you're going to have temperature that is going increasing in this direction, and in that particular graph the pressure is also increasing if we go down. And this shows where ice can exist as a solid, a liquid, or a gas. Okay, so notice that under very high temperatures that water is going to exist as a gas. So up here is water in its gaseous phase. And then over here, this is going to show you how water exists as a solid. So we're going to have a line that kind of goes down like that. And then this is going to be the solid phase of water. And then this over here is going to be the liquid phase of water. And what has this got to do with glaciers? Well, glaciers are going to be composed of water, and it's normally going to be frozen water. But the deeper that you go inside the glacier, the greater the pressure is going to get because there's more stuff on top of you. So let's find out how would that affect whether or not the material, the water, is in the form of a solid or whether it's in the form of a liquid. So in this picture here, it shows at 1 atmosphere of pressure. Okay, so that's going to be this red line that is going sideways. And so this is going to represent 1 atmosphere of pressure. So that would represent up at the top of the glacier where there is not very much pressure. Okay, now let's pick out a temperature. So I'm going to just pick out a temperature of like -5 5 degrees Celsius. So let's just, for example, call this temperature right here a -5 degrees Celsius. And then if we were to take that and move it up to here, okay, that means that under 1 atmosphere of pressure and at -5 degrees Celsius, water is in what state? It's a solid. So you're going to have solid ice. Okay, but look at what can happen if you're deeper in the glacier where the pressure is greater. So let's go down to, let's say, down to here, and this represents a pressure that is going to be greater than 1 atmosphere. So it's going to be a higher pressure deeper into the glacier. So if we were to take this thing over to the same temperature, -5 degrees, notice that it plots right about there. And notice now it's a liquid. So if you increase the pressure on ice, it will liquefy. So an example of this would be an ice skater. Have you ever wondered why do ice skaters have very, very thin blades underneath their feet? Okay, we did a little experiment with the pencil, and we pushed the pointy end of the pencil on our finger, and we found that that hurt a lot because that exerted more pressure than if you used the rubber end of the pencil. So the blade of an ice skater's shoe provides a lot of pressure on the ground, on that ice, and it liquefies that ice, changes from a solid to a liquid, and they're actually skating on top of that water. The glacier will do the same thing. So underneath the glacier, the pressure can be so great it can liquefy the ice that's down there, and then that makes it easier for the glacier to move downhill. And again, whether or not it's acting like a solid or a liquid or something in between. So if it's not quite solid and it's not quite liquid, we would say it's plastic. So at different levels inside the glacier, it starts out being completely solid, and then if we increase the pressure enough, it turns into a liquid, and then halfway in between, it's behaving like a plastic, and it's moldable. So in this picture here, notice that that's a picture that is showing, this is the surface of the glacier, and then this is what the glacier looks like as you go inside of it. And then what they did was they made a hole that went straight down into the glacier. And then as the glacier moves downhill, you notice that some parts of it are moving faster than others. So that this thing that was used to be straight up and down, eventually as it goes downhill, starts to curve like that. And so again, this is also very similar to what a river does. So as a river is rubbing up against the sides of its channel, it's moving the slowest at the sides of the channel, and then deeper or away from the sides, it's moving faster. So you notice that it's moving the slowest as it's rubbing up against the bottom of the slope that it's going down. So the point is that gravity is going to pull the glacier downhill. Ice, depending on its pressure, can move at different speeds, because at some places it's moving as a solid, other places it's moving like a plastic, other places it's moving like a liquid, and then ice moves at different speeds at depth. One last thing before we go on is notice that up here at the top, where it is completely solid, it can crack, it can fracture. So again, going back to stuff that we've already talked about, we talked about how rigid rocks fracture, and that produces earthquakes and faulting. But at depth, where the pressure is greater, the rocks tend to bend and they tend to fold. So up here at the top, the rock, this isn't rock, this is ice, but it tends to break and fracture. And so this is where we get crevasses from. So the ice can actually split apart up here, and it can be very, very dangerous because those cracks can extend a great deal into the glacier, and then it can get covered up by snow. So that if you're walking along on the surface of the glacier, you might come into one of these cracks and you might fall into it. And so it can be very dangerous. So I just wanted you to notice that up at the top, where it's behaving like a solid, it tends to crack, and then it tends to flow further into the glacier. All right, so let's take a break, and when we come back, we're going to talk about how do glaciers erode and transport material.